In the last video, we defined what it means for a matrix to be in row-reduced echelon form. We're going to discuss two facts about row-reduced echelon form. The first is that if you've got any matrix, then you can find a sequence of row operations so that when you do those row operations to your matrix, you end up with a row-reduced echelon form matrix. You can find a proof of this in the lecture notes and a proof of the second fact as well, but it's not too difficult to convince yourself of the truth of fact one. So look at the definition of row-reduced echelon form, which I've copied at the bottom here. You'll see that it consists of 4 properties, and if any of these properties was false for a particular matrix, then you can fix it by doing some row operations. For example, if property 1 failed, if you had a leading entry which wasn't 1, you could just multiply the row of that leading entry by 1 over the leading entry, and that would change the leading entry so that it was 1. So we can fix property 1 by doing a single row op for each leading entry which isn't 1. Property 2 asks for every 0 row to be at the bottom. You can fix this by doing the row operation which swaps 2 rows. So if you've got a 0 row, you can swap it so it's at the bottom. Property 3 asks for all entries in the same column as a leading entry to be 0. So for example, you might have a leading entry here. Let's say your leading entry was 1, but you had something above it, like you had a 2 there above it and a -1 below it. And then you could fix this problem just by adding multiples of the row containing the leading entry to the other rows to eliminate those non-zero entries in the same column as your leading entry. So in my example here, you'd subtract 2 times this row from this row, and you'd add 1 times this row to this row, and then the other entries in that column will be 0. So property 3 can be fixed as well just by doing row operations. And finally, property 4, which says that the leading entries must go from left to right as you read from top to bottom down the matrix, that can be fixed by swapping rows. So property 1 is pretty intuitive. Property 2, at least for me, is not very intuitive at all. It says that if you've got 2 row-reduced echelon form matrices that you can get by doing row operations to a single matrix A, then actually those row-reduced echelon form matrices must be the same. So in other words, there is one and only one row-reduced echelon form matrix which you can get to by doing row operations to your chosen matrix A. So that uniqueness property is really not obvious. You can read a proof of it in the online notes. But the fact that there is one and only one row-reduced echelon form matrix which you can get to by doing row ops to a matrix A justifies people talking about the row-reduced echelon form of a matrix. What they mean when they say that is the one and only one matrix which can be obtained from A by doing row ops to it. Okay, let's try an example then. So let's try an example of getting a matrix A, so here is my matrix A, and doing row operations to it until you reach a row-reduced echelon form matrix. So I've got my matrix and I want to do row ops until I reach a row-reduced echelon form matrix. So what should I do? If I look at this thing, I can see that I've got just here a leading entry in row 1, and the leading entry is 1, so I'm happy about that. What I'm not happy about is that there are other entries in the column of that leading entry which are not 0. So I should use the row operations which subtract multiples of row 1 from other rows to eliminate the non-zero entries in column 1 which aren't my leading entry. So let's do that. So we'll begin by subtracting multiples of row 1 from row 2 and row 3. So we'll do the row operation which sends row 2 to row 2 minus 4 row 1. Okay, so what do we get when we do this row operation? When we do this, we get, well, row 1 won't change and row 3 won't change either. But what will change is the middle row. So let's think what's going to happen in the middle row. I've got to do some arithmetic. I'll get a 0 here, and then I do 5 minus 8, which is minus 3, and 6 minus 12, which is minus 6. Okay, so I've not finished eliminating the non-zero entries in the same column as the leading entry in position 1, 1. So I need to do the row op, which sends row 3 to row 3 minus 7 row 1, so that I eliminate that 7 in position 3, 1. Okay, so let's do it. What happens? Row 1 won't change, row 2 won't change, and row 3 will change. And in row 3, I'll get a 0 here, and the next I get 8 minus 7 times 2. So 8 minus 14, which is minus 6, and 9 minus 7 times 3, 9 minus 21, which is minus 12. Okay, so are we in row-reduced echelon form? The answer is no, we're not in row-reduced echelon form yet, because if you look at the leading entry in row 2, there is a leading entry here in row 2, and that leading entry is not 1. So we have to change row 2 so that the leading entry is 1. So to do that, I'm just going to multiply row 2 by minus a third. So if I do the row operation which multiplies row 2 by minus a third, I'm not changing row 1, and I'm not changing row 3. And what will happen in row 2 is that I get 0, 1, 2, like this. Okay, again, we're not in row-reduced echelon form, and again, one of the reasons that we're not in row-reduced echelon form is because there's a leading entry at position 2, 2, and the other entries in the column of that leading entry are not 0. So I need to eliminate the 2 in position 1, 2, and the minus 6 in position 3, 2. So we're going to subtract 2 times row 2 from row 1 to eliminate the 2 in position 1, 2. So we'll do row 1 goes to row 1 minus 2 times row 2. Okay, where does that take us? It doesn't change row 2, and it doesn't change row 3. And what happens to row 1 is I get a 1 there and a 0 there, and what have I got? 3 minus 2 times 2, that's minus 1. Okay, so I still have a leading entry. I still have a non-zero entry in the column of the leading entry in position 2, 2. So this thing here is a non-zero entry in the column of the leading entry in position 2, 2. So I've got to get rid of that, and I'm going to do it by by adding 6 times row 2 to row 3. So row 3 is going to go to row 3 plus 6 times row 2. Okay, what happens? We don't change row 1, we don't change row 2, and in row 3, I'm adding 6 times row 2. So I get a 0 here and a 0 here, and minus 12 plus 6 times 2 is 0. And at this point, we have now reached a matrix in row-reduced echelon form. So the leading entries are here, and they're both 1. The 0 rows are at the bottom, so there's only 1 row of zeros, and there it is at the bottom. It's below any non-zero rows, so we're happy about that. The leading entries, the entries in the column of any leading entries are all 0. So we've got a leading entry in position 1, 1, and all the other entries in that column are 0. And the other leading entry is in position 2, 2, and all of the other entries in that column are 0. And finally, the leading entries really do go from left to right as you go from top to bottom. So the leading entry in row 2 is strictly to the right of the leading entry in row 1. Therefore, this matrix is in row-reduced echelon form, and we are done.